everyone! Welcome to the second video on vectors, 8.7. Today we're going to be talking about vectors on the coordinate plane. So we're taking what you learned in the last video about vectors and now we're going to slide these vectors over onto a coordinate plane. Vectors can be in standard position on a coordinate plane. That's if the initial point is at the origin, like the picture on the screen right now. The initial point where the vector is starting, it's right on the origin, right at 0, 0. So this vector is in standard position. If someone were to tell you that this final point P here of this vector was, let's give it some numbers here. Let's say that this is maybe over 4 up 3. So if someone were to tell you, hey, I've got this vector, and I've plotted this vector on the coordinate plane, and the initial point is at the origin, and the final point of the vector is at 4, 3. What are some things that you could tell about the vector if you knew that information? You could tell how long the vector is. We're not going to do that right now, but we're going to do it later. You can tell how long the vector is if you know that it starts at the origin and if it goes until the point 4, 3. You could also tell the direction of the vector. You could tell if it's going off to the right or to the left or to the bottom. And you could describe that direction by using an angle measurement. You could say, oh, this vector is 30 degrees west of something, or this vector is 86 degrees left of the horizontal. So you could describe the direction of the vector. You could describe the length of the vector. So in order to do that though, you would either need to know where the vector starts and stops. So you would need to know both points. Or if you know that it starts at the origin, then you just would need to know the ending point, because if it starts at the origin, the beginning point is going to be 0, 0. So what we're going to do today is we're going to start with vectors that are actually not going to be at the origin yet, but we're going to, step 1, move the vectors on the coordinate plane so that they are at the origin, and then once those vectors are at the origin, then we can talk about doing some of these other things with the vectors too. Once we move a vector so that the initial point is at the origin, that vector is going to be in component form. Component form is written kind of like 4, 3, but instead of with the parentheses, we would just write it with kind of like arrows, I guess. So it would be 4, 3 like this, kind of like with parentheses still, but they have to have a point there. That's going to be the component form of this vector. So it means that the initial point is going to be right here at the origin, and it's going to go to our point 4, 3. Now, maybe the vector didn't start off that way. Maybe the vector was somewhere else on the coordinate plane, and we kind of shifted the vector so that this is where it's going to end up. So the component form is kind of like a temporary form of the vector. Maybe that's not where it really is, but maybe we're just kind of putting it there so that we can find the direction, or so that we can find the magnitude of whatever the vector is. So let's take a look at an example. Here's a vector that's laid out on the coordinate plane for us. If we zoom into this picture here, we notice that this vector is not currently at the origin. We want to scooch this vector down a little bit and to the left a little bit so that this point right here, the A, we want it to be exactly right here on the origin. So to do that, we're going to need to shift the entire vector to move this point to the origin. We need to move it to the left by 1, and we need to move it down by 1. So I need to do that to every single point on the vector, including this final point here, the B. It needs to move to the left by 1, and it needs to move down by 1. So the final point of the vector is going to be right here. Let me highlight that. This is going to be the final point of the vector right here. So now we know where the initial point should be. We went over 1 and down 1. And now we know where the final point should be. We went over 1 and down 1. So now in yellow, I'm going to draw what the vector should look like. This should be the component form of the vector. So the component form of the vector is the same vector, the same direction. We didn't move the angle at all. It's the same direction, it's the same length. We just shifted the vector so that the starting point of the vector has to be at the origin. Once you shift it and you make the starting point at the origin, now you can figure out what the component form of the vector is. The component form is always going to be x comma y, and you're always going to find out whatever the final point of the vector is and write that in the component form. So the x, let's see, 1, 2, 3, 4, 5, and the y, 1, 2, 3, 4. So the component form of this vector is 5 comma 4. Now that we have put this vector in component form, it's going to allow us to do so many more things with it. But we're not quite ready for that yet. Let's practice a couple more problems where we're going to have a vector, and first we have to scooch it on the coordinate plane so that the initial point touches the origin. Then we have to write down what the component form of the vector is. All right, so there's two problems here for us to practice with. You can actually try these problems on your own if you would like to. For both of them, you just scooch them so that their initial point is touching the origin, and then you're trying to write down what is the component form of the vector. If you want to try it yourself, you can go ahead and pause the video now, and then in a couple seconds, when you unpause it, I'm going to give the explanation for how to do that. I'll start probably with the red one. All right, so this red vector here, I'm going to need to move both points up by 1. When I move this C up by 1, it's going to touch the origin. So that means that the final point, I also need to move up by 1. If you move them up by the same amount, then it keeps everything else in the vector the same. Or if you move them down by the same amount, or if you move them to the left by the same amount, as long as you move both points the same, then the vector is not going to change. So I'm moving both points up by 1. That way the starting point can be at the origin. And then I'm going to draw the vector from here to here. So that's going to be my answer. I also have to write down the component form of the vector. It's always going to be x and then y. In this case, the component form is going to be 4, 2. All right, now I'm going to do the blue one. If you haven't tried one on your own yet and you want to try the blue one on your own, go ahead and pause the video now. Give yourself a little bit of time to try the blue vector. All right, let's talk about this blue vector here. I want to get this initial point that I just circled to the origin. To do that, I have to move it to the right 1 time, and I have to move it down 3 times. So I'm going to do the same thing to the final point of the vector. I'm going to move it to the right 1 time, and I'm going to move it down 3 times, and my final point is going to end up right here. Now I'm going to draw the vector from the origin to this final point that I just discovered. And now I'm going to write down the component form of the vector. It's going to be -2, -4. That's the component form of the blue vector. Do you guys remember at the beginning of the video I said how once you find the component form of the vector, it allows you to do some other cool things too? Well, that's what we're going to do for the last part of the video today. We're going to start with this example, and we're going to write it in component form, which is what we've been doing. And then after we write it in component form, we're going to be able to do something else with it that's pretty cool. So first, let's write it in component form. To do that, I'm going to take this initial point R, and I'm going to move it to the origin. To move the point R to the origin, I need to move it over 1, 2, 3, 4, 5 times. And I need to move it up 1, 2, 3, 4, 6 times. Okay, Now, I don't really have enough space to do the S on my coordinate grid, so I'm just going to go ahead and do this here. So my initial point R is now at the origin. I moved it over 5 times, and I moved it up 6 times. I need to take this point S, and I need to move it the same amount. Right now, point S is at -3. If I move it over 5 times, it's going to be at +2. And I need to move it up 6 times. Right now, point S is at -1. If I move it up 6 times, it's going to be at +5. So the final point for my vector S is going to, this is not really to scale, sorry about that. It's going to be 2, 5. This is what the vector is going to look like. It's going to be 2, 5. Now remember, this is the component form of the vector. It's not the real vector. It's just we scooched it on the coordinate plane, and now this is where it ended up. It's going to be 2, 5. Okay, but once you do that, you can do 2 cool things. Now we're actually just going to do one of the cool things in this video. You're going to have to wait until the next one to do the other thing. So one of the cool things that you can do once you know the component form of a vector is you can find the magnitude of the vector. Remember what magnitude is? Magnitude means size. You can find the size of the vector. Now, we don't know anything about this vector. We don't know if it's 5 inches per second or 24 miles per hour. We don't know what the size is. So since we don't know anything about this vector, we're going to just say, you know what, the length of the vector, that's going to be the size. So we're going to find the length of the vector. So we need to find the length of this line, or this ray kind of. How can I find the length of a line on a coordinate plane? If it wasn't a vector, if it was just a regular line segment, and if I knew that one of the points was 2, 5 on one end point, and if I knew that the other end point of the line segment was 0, 0, how might we find the length of that line segment? We could actually do it a couple different ways. We could do it using the Pythagorean theorem. If we wanted to draw a triangle right here, this is now a right triangle. This is our 90-degree angle. This side length is 2, this side length is 5. So you could use the Pythagorean theorem to find x. That's one way to do it. Another way to do it is to use the distance formula. Do you guys remember the distance formula? It's x2 minus x1 squared plus y2 minus y1 squared. Add them together and take the square root, the distance formula. So that's what the distance formula is. So we can also use that if we want to try to find x. Now we know x is going to be a positive number, so if we use the distance formula to find the length of this line segment, we're going to want to choose the 2 to be our x2, and then the x1, the y1, that's always going to end up being 0, 0, at least in this problem, it's going to be 0, 0 here. So we're going to do 2 minus 0 squared plus 5 minus 0 squared. And then I'm sure you guys can kind of see, hey, isn't this kind of going to be the same thing as the Pythagorean theorem? Because in the Pythagorean theorem, we're going to take 2 squared, and we're going to add it to 5 squared, and then we're going to take the square root to find the hypotenuse. So it's actually going to end up giving us the same thing either way. So there's 2 different ways that you can solve it. Let's keep going. So let's see, this is going to be 4 and 25. So our final answer is going to be the square root of 29. And since I do not have a calculator here, I'm just going to leave it as a square root. There is not a way for me to simplify that radical expression because nothing times nothing is 29. So I'm just going to leave it as a square root of 29. Or you can write it as a decimal. You can read what the textbook says or read what iExcel says. They'll tell you how they want your final answer to be. But for now, we're going to say this is the magnitude, this is the size, this is the length of our vector. It is the square root of 29. We only have one last problem in the video. The last problem is right here. Notice it's the exact same thing as the other problem, so there's two directions. The first direction is to write down the component form of the vector, and the second direction is to find the magnitude of the vector. Once we're done with this problem, we are done with the whole video. Go ahead and pause the video now, try this last problem on your own, and then I'll go ahead and give you an explanation and show you the answer. All right, when we write the vector in component form, we're going to scooch this point K so that it's right where the origin is. It's going to need to go up 2 and over 1. So I'm going to take this final point here and I'm going to make it go up 2 and over 1. So the final point of the vector is going to be right there. And then I'm going to draw it. This is what it would look like. The component form is going to be x comma y, and it's going to be where the vector ended up. And it ended up right here. So that is 1, 2, 3, 4, 5, 6, -6, -3. That's the component form of the vector. So that's number 1. Number 2, find the magnitude of the vector. You can either complete the right triangle like this, or you can do the distance formula. They're both going to give you the same answer, basically the same way as well. This is a 6, this is a 3 because that side is 6 units long. This side is 3 units long. We're trying to find out what the hypotenuse is. So 3 squared plus 6 squared is equal to the hypotenuse squared. So 9 plus 36 equals x squared. So 45 is equal to x squared. And then to solve for x, I would square root both sides. So x is going to be the square root of 45. Now you have two choices. You can either simplify the radical expression or you can make it a decimal. If you simplify the radical expression, 45 is equal to 9 times 5. Since 9 is a square, I can pull the square on the outside of the square root. And so that's going to be 3 times the square root of 5. So the magnitude of the vector, the length, the size of the vector is 3 times the square root of 5. All right, that's it. Make sure to submit your notes on Canvas. Bye guys, have a great day.